Okay, I left you with this little thing to think about why are these clusters of stars dispersing over time when the whole cloud and star formation region should have been bound by gravity initially. So the key here is to realize that star formation is actually quite an inefficient process. So only about 10% of the mass of the original collapsing cloud will end up in stars, and the rest stays in the gas phase. And of course, that gas is mostly then blown away by the expanding H2 regions. And there are also some phenomena like stellar winds coming from these hot stars as well. So everything gets blown away and cleared out. So, so for example, even if you started out with a molecular cloud that had a mass of 10,000 solar masses or something like that, only maybe about 1,000 solar masses would end up in stars, and the other 9,000 solar masses are dispersed away. So most of the mass is actually blown away again, and so therefore there's not enough mass now in that volume to keep everything together by gravity. So hence the resulting star clusters will just disperse over time and drift around. Okay. So we'll just want to finish up with some sort of zooming out views and start to get a more global picture of what our galaxy and other galaxies look like in these kind of at radio wavelengths. Okay. So I'm going to start with some quick views of our galactic plane, so the Milky Way itself. So remember that we live in a spiral galaxy, and we are in the plane of that spiral galaxy, which is a disk. And so when we look out along the galactic plane, along the Milky Way, then we're looking through our own galaxy. And so you get a lot of sources stacking up along the line of sight because you're looking all the way through the plane of our galaxy. And here's a recent survey of the galactic plane with the Very Large Array at around about 5 gigahertz. And you can see it's packed with radio sources here. Some very large ones, lots of smaller ones. These would be mostly in these complexes, and clusters would be star-forming regions and a lot of H2 regions. But there are other things in here. All the massive stars are in the plane of our galaxy, in the spiral arms, but again, we don't see the spiral arms because we're looking through the plane. And so you're going to get all the exploding massive stars that explode as supernova remnants in here as well. And you will also see some other objects like Planetary Nebulae that we will come back to in a moment. So, it's quite a busy region in terms of radio sources when you look along the galactic plane. And of course, you also get this dust-free view, so you can see all the way through our galaxy, even though all of the molecular clouds and that are in the way here. So you don't see a lot of any of this stuff, or very little of it in the optical. And to bring us right up to date, here is the first look at our just a small portion of our galactic plane with the new Meerkat array in South Africa, the forerunner to the SK mid array. So this is an image at around about 1.4 gigahertz of just a snippet of the galactic plane. So you can see just full of these extended sources. So many of these types of structures here would be H2 regions, whereas some of these other more extended sources like this are likely to be supernova remnants. And of course, you see the rest of the sky as well. So you've got things like double load radio galaxies in here. So these are extragalactic sources that are, obviously way much further away than our galaxy. In fact, most of these point sources here would be extragalactic. Okay, so I now want to just look a little bit at views of other galaxies, sort of nearby galaxies. So let's look at the right image here first. So this is an optical image. So you can see this is a spiral galaxy. It's actually a galaxy called M33, which is one of the galaxies in our own local group of galaxies. So this is only about 1 megaparsec away. So as you can see, it's sort of close to being a face-on sort of spiral galaxy. So you can see spiral arms coming out here and coming out here. And the purple colors here is an image in the strong emission line in the optical, H-alpha optical emission line, which again, if you can see H2 regions in the optical, this line is very strong. So all these circled objects here, in fact, most of these purple objects that you can see tracing the spiral arms are H2 regions. So characteristic of spiral arms that the massive stars are formed in the spiral arms. They only live for a few million years, and so they also die and explode as supernova in the spiral arms as well. So here is a new sensitive image of this object, again with the Very Large Array at radio wavelengths. Okay, and so you can see, the scale is the same here. So you can see some of the same objects being picked out. So this long line is a spiral arm here, and most of these objects here are H2 regions, and you can see the same structures here. Again, this very bright H2 region complex here showing up as very bright here as well, and you can see the northern sort of spiral arm coming in this way as well. So in this radio image, the color again represents this idea of spectral index, and so you can see that most of the yellow objects here have a spectral index of around 0, so they would be these optically thin H2 regions that we've talked about. Okay, and so you can see that they're really sort of dominating things in this particular wide field image here. We can also zoom in now on this little portion here. So this sort of nice bit of spiral arm that you can see quite well defined there in the next image, this one. So here's a cutout portion of that spiral arm that we can see in this nearby galaxy. So again, all the yellow objects here are the H2 regions again. But you can start to see some other sort of bluish sort of objects like these, like these. So if we go back, anything with a sort of bluish spectral index is negative, and that will be a synchrotron emission from a supernova remnant. And the white circles represent sort of other evidence that these are supernova remnants as well. Okay, and so you can see they line up as well. Again, an optical image here. This is a different optical image with various emission lines. But again, the yellow objects are H2 regions. The bluish, purplish objects here are supernovae, and so you can see them showing up here. Okay. So you've got this real mix in spiral arms of H2 regions, which are at the beginning of massive stars' lives, and supernova remnants, which are at the end of massive stars' lives, but they all trace the spiral arms in spiral galaxies. So this is classic, what we would call population 1 traces, population 1 being young massive stars. So just to recap, the idea that you've got these different slopes of the radio continuum spectra for the thermal H2 regions that we've looked at principally in this lecture, okay, compared to the sort of negative power law slope that you get for a synchrotron source, a non-thermal source like a supernova remnant. And so again, the spectral index across here, if it's negative, non-thermal, probably a supernova remnant in the galactic case. If it's thermal, positive, then it's going to be an H2 region. So just a final few words on the idea of using H2 regions, particularly and supernova remnants for that matter, to sort of trace star formation, throughout the universe. So, of course, H2 regions and supernovae are only ways of tracing the formation of massive stars. So does it really trace star formation as a whole? Well, we think it does. So even though they are rare, we think they are good tracers of the whole of star formation, even the formation of stars like our sun, the lower mass stars. And this is where radio astronomy really comes into its own, because we can use these sensitive, high-resolution radio studies to find these H2 regions in supernovae, not only throughout our own galaxy, but through other galaxies as well. And of course, it gives you this extinction-free view. You don't have to keep worrying about correcting for dust obscuration at radio wavelengths, because there isn't any. Now, so why do we think that just studying the formation of massive stars is okay? Well, there's a concept in astrophysics called the initial mass function. Again, I'm not going to go into this in any detail, but it's basically a curve that looks like this. So it's the number of stars per logarithmic mass bin, in a population, and it's the initial mass function. So it's the distribution of stars by mass when they're born, effectively. Okay. And so you can see here, this is logarithmic. So this is the high mass end. Okay. So this is 10 solar masses up to 100 solar masses. So this is just the end of the distribution that gives rise to these H2 regions and supernovae remnants from the massive stars. But most stars are at lower mass. But luckily, we think that this so-called IMF, is reasonably constant across different locations in the same galaxy, and also across time, as we look back in time at more distant galaxies. There are likely to be some changes, but they're not drastic. Okay, so therefore, in a sense, by studying H2 regions and supernova remnants, we're only really tracing this end of the initial mass function, but as long as it stays reasonably similar throughout cosmic time, then we're basically tracing the whole of star formation. So that concept will come back, I'm sure, when we're looking at the evolution of galaxies. So I just want to finish up on one more type of source, which are quite nice sources as well, and show up very well in the radio studies of our own galaxy, for sure. And these are planetary nebulae. So these are nothing to do with planets. They are basically, again, another example of a photoionized nebula, but it's at the end of a star's life. Okay, so particularly sort of intermediate mass stars, so stars that are sort of 1 to 10 solar masses. At the end of their lives, they eject their outer envelopes after the sort of red giant phase and leave behind a hot compact core that will eventually become a white dwarf star. But during that ejection phase, the hot core photoionizes the ejected envelope. And again, so you get something very similar to an H2 region. So you get an ionized envelope of gas. So it's really very similar to an H2 region. The physics is exactly the same. Okay. But it's to do with the end of a star's life and not the beginning, like an H2 region. Okay. So here are a couple of optical images of planetary nebulae. They're very pretty looking objects. So you can see this idea of an ejected shell of gas here in both of these objects that is lit up in the optical, and you can actually see the central hot star in both of these as well. So in here, that's, you've got a shell of ionized gas here, which is fluorescing in the optical, but in the radio, we can see examples of these objects. So this is from some recent work with the VLA, and so you can see these nice shells of or elliptical shells of ionized gas, and so these are all examples of planetary nebulae in our galaxy. And so again, they tend to be focused along the galactic plane. Okay, so just to summarize, spiral galaxies like the Milky Way contain many of these extended radio sources. I haven't been talking about any type of point source here, radio stars or pulsars or anything like that. You'll get a subsequent lecture on pulsars. So we're talking about kind of nebular sources, extended regions of ionized gas. And so we've seen that the H2 regions trace the birth of massive stars in galaxies. Supernova remnants mainly trace the death of massive stars. Of course, there are other types of supernovae from interacting binary systems that are nothing to do with massive stars, but let's leave that to one side for the moment. And briefly there, we also just saw that these Planetary Nebulae, which again are examples of photoionized nebulae that emit radio free emission, trace the death of intermediate mass stars. And throughout this lecture, we've seen this idea. We've introduced the idea of optically thick and thin emission regions for the H2 regions, introduced the idea of a spectral energy distribution, and again, come back to this notion that looking at the slope of the radio spectral energy distribution through spectral indices is a good way to differentiate between different types of source, whether they're optically thick or thin, and whether they're thermal or non-thermal, whether they're emitting free or synchrotron radiation. So after this lecture, we will be going to looking at sources in the radio sky that are very much of a non-thermal nature. So we'll leave the thermal radio sources for a while. Okay, thanks a lot.